So hello everyone, we will be starting soon the session of paper presentations on inverse problems. So it's like on Monday, 4 minutes per paper presentation, and then we have a nice time for the oral discussion. And this session will be chaired by Cheng from Duke, so I will let her the stage from now.
Okay. Thanks, Nanka. Thank you very much. Okay. I guess we have already the first speaker ready. So I think from the channel, I'm still waiting for two people presenting second and third paper. So if they're here, like Juan, maybe we can please let me know. Otherwise, we will just let the other people present the paper, and we have some time for the discussion, encourage questions. Okay. Oh, okay, cool. Okay, great. Okay, so the first speaker, the first paper today will be the spectral geometric matrix completion presented by Mead Borowski from Technion. Okay, please go ahead, Mead.
Yeah. Okay, you can see my screen. Everything is okay, right? Yeah, can you hear me?
Yeah, we hear you.
Okay, good.
Yes, we hear you.
So hello, everybody. I'm presenting a work I did with Sanket Vedula and Alex Bronstein about matrix completion on graphs, hence the spectral geometric term here. So let me start by formulating matrix completion problem. There's a matrix, there's a bunch of entries that you know, and you're interested in estimating the rest of the matrix. So here, M is the ground truth matrix, S is this mask that encodes the entries that you know, and X is the unknown matrix. So one way to approach it is to formulate some optimization problem. Because this is a nil-post problem, you need some regularization here in the form of a rank. So you're trying to minimize the rank of the matrix such that it fits all the measurements. And there are a couple of ways to solve this problem. I mean, this is an intractable optimization problem because rank is it's a discrete and it's a non-convex objective. So one way to approach it is to relax this rank penalty into its convex envelope. So you replace the rank with the nuclear norm. It's just a sum of singular values. Now you have a convex problem. You can solve it. You get a global minimum, but the problem is that this relaxation is not always tight. It depends on the number of measurements that you have. And usually in applications, you don't have that many measurements to satisfy the guarantees. Another way is to explicitly factorize the matrix as a product of two factors. So these will be narrow factors such that the product matrix will be low rank. The problem here is that first, it's not a convex problem, but maybe more importantly is that you need to specify the rank in advance. And there's a third alternative. It's kind of a new technique that factorizes represents the matrices as product factors. And now these factors don't have to be low rank. It can be just full dimensional matrices. And you just optimize this objective using stochastic, just using gradient descent without any constraints. So let's focus on this objective. What makes it useful is that it was recently shown that if you just apply gradient descent on this objective, you get that the singular values of the product matrix evolve according to this differential equation. So effectively, there is some kind of implicit regularization that forces this matrix to be low rank. Let me show you some example. I took it from Aurora's paper, Aurora et al.'s paper. So if this factorization is just using a single layer, single matrix, then all the singular values evolve at kind of the same rate. But if I increase the number of layers, I increase the depth, then there starts to form some gap between the evolution rates of the large singular values and the small singular values. And if I increase it even further, then there's a larger gap. So the first singular values, the larger one, converge pretty fast. And the smaller singular values, they don't even converge at all. Effectively, the matrix that you get out of it is low rank. And this is not a complete description of the evolution of singular values because it also depends on the singular vectors throughout the optimization, which is unknown. and also depends on the specific choice of the loss function. Okay, it doesn't have to be an L2 loss like this. And this is what we're going to do. We're going to mess up with these loss functions such as to control the evolution rate. So we are dealing with in this work, we're dealing with a geometric matrix completion problem. Here we assume that there is some underlying geometry. So this matrix, it's accompanied by a set of graphs. There's a graph representing a relationship between different rows and a graph representing the relationship between different columns. This is, for example, very popular in recommender systems where you have on the rows you have users and on the columns you have items. And the assumption is that similar users are going to give the same rating to the same item, or similar ratings to the same item, and same thing can be said about the items. Similar items are going to be assigned the same rating. Okay, so here, when we have this additional information, we can think of this matrix completion problem as some problem occurring on the graph. We can model the matrix as a signal living on the product graph. And now it becomes a structured low rank matrix completion problem. So we can model the matrix X as a band limited function on this graph. Basically, we think of it as being represented as a linear combination of the first harmonic functions on this product graph. Okay, so the bottom line is that our data term now becomes something like this. We just over-parameterize the matrix as a product of three matrices. And in order to take into account this, structure, this graph structure, we also add a smoothness term, which is just regular differential energy. And here, what we did is we parameterized everything in the eigenbasis of the Laplacian. The benefit is that the Laplacian basis, the Laplacians of these two graphs are becoming diagonal in this basis. But you can just use the regular basis as well if you want. And this is what we call spectral geometric matrix completion. It's basically it's deep matrix factorization with some geometric regularization. And you can appreciate how simple this formulation is. It's basically just an optimization problem. Or if you want to think about it as a deep linear network that just has 3 layers, everything is linear here. And by virtue of this theorem on the convergence rate of the singular values, you get that this matrix out of this optimization problem will be both smooth on this product graph and low rank. We have some extensions also in the paper. We have what we did here is we squeezed in between the factors 2 diagonal matrices that act like spectral filters. So you can control the bandwidth of this filter by deciding how many elements in the diagonal you have. And by doing that, we were able to achieve some kind of inseparable filter that mixes between smoothing along the row and smoothing along the columns. And we get much better results, much more robust, and depends on, you can use less number of measurements to get the same error rate. And we call this method SGMC-Z. Z stands for zoom out because we took inspiration from some papers that we and our colleagues did in the field of shape processing. Essentially, this loss, what it does is that it injects a kind of model into the matrix completion problem. We also add this term here below that adds some regularization on the individual layers. Now, all this stuff here, it's kind of an extension above the regular DMF, so maybe the theory doesn't cover it, but in practice, we see that we get the same kind of evolution. So I decided to focus only on a single slide here because of the lack of time, just to show the applicability of this method. So we do something called cold start analysis, in which we kind of stress test the algorithm to see what happens when we eliminate eliminate elements from the matrix. So what we do is we choose a couple of rows corresponding to users, and we decide how many ratings to eliminate from each of these users. So we retain either 10 ratings, 5 ratings, or 1 ratings. It's a very extreme case. And you can appreciate here that even in this very extreme case of 500 cold start users, and only like 1 rating, 5 ratings, or 10 ratings, we get pretty good results. I mean, it's very robust to the elimination of data, much better than just using the plain DMF. But also in the paper, we show that it's better than other very complicated methods that use complex architectures. And this is just a very simple and basic architecture that can be written in a few lines of code and achieves as good or even better results in state of the art. Okay, so you can have a look at our paper, and we have also a Google Colab notebook in which you can play with this algorithm, and the code is here. Thank you.
Okay, thanks. Okay, we'll actually try to move on the next talk and save the discussion, unless there was some immediate question now. Maybe we'll save the discussion to the later time. Okay,
yeah,
so we have a
fine.
tight schedule. Okay, thanks. Okay, very good presentation. So on the, okay, so the second paper is the we're presenting today is solving Bayesian inverse problems, vibrational autoencoders. I guess Jonathan Whitmer is Jonathan Whitmer.
Yes.
Okay, he's going to go present the paper. Okay, great. Let's see, Jonathan. You there?
Okay. Yes.
Okay, great.
Can you
Please
see the
start.
screen all right?
Yes, I can see the screen.
Okay, great. So this is some work that we've been doing with collaborators Huan Go, Schroeder-Sheriffstein, and Professor Tan Boitan at the Odin Institute at the University of Texas. And so what we want to do is we want to learn inverse problem solver that takes in observations y and then gives us a parameterized probability density on the parameters u that that we're looking to find. And so given we want to find the parameters phi of the parameterized distribution q that approximates our posterior distribution p of u given y. And so a significant contribution of our work is to show that this equation 1, minimizing this equation 1, upper bounds equation 2. And so equation 2 is really is exactly the task of variational inference. The equation 2 gives us a notion of distance between our approximate posterior q phi and the true posterior p of u given y. And equation 1 is in terms of things that we already know and lends itself to an optimization problem. So we find and show that the minimization of the target 1 yields an optimization problem of a form equation in 3. So you can see 3b corresponds to a prior term. The second term in 3a is a likelihood term. And then we have this additional third term here that allows us to encode information about what the true parameter is supposed to be, u of m. So if we have a data set of parameter u and observation y pairs, we want to be able to include information of what that is into our optimization problem. And so this allows us to learn a solver that allows us to quickly get an estimate of u for an unknown u given new observations y. And so we use a neural network to do this, and it's parameterized by the weights of the neural network w, but more generally, just phi. So schematically, this is what it looks like. You pass in observations y into the neural network, and then it outputs the mean for Gaussian distributions. It outputs a mean estimate in u post and a representation of the covariance matrix gamma post here. So with this information, these parameters, we can take draws from our approximate posterior, push them forward through the forward map of whatever our forward problem is, and then compute this loss function. So directly from the mean and the covariance, we can compute the prior misfit or the prior term here, and then we have our data misfit to the data that we have for the UI pairs, and then we have our likelihood here, which in our case we typically do physics-based inverse problems, PD constrained inverse problems. So in our case, f is going to be a partial differential equation. So another benefit of our framework is that it's adaptive. We have the JS divergence that we use, the Jensen-Shan divergence. It's parameterized by the single scalar alpha that allows us to choose what we mean by distance between our approximate distribution q phi and the true posterior distribution p. And so by tuning this one scalar, we can push the solution towards solutions that make more sense for the particular problem that we have. And this will make more sense in this concrete case. We're doing a heat conduction problem. So we're observing the temperature at the points of the red cross. We have sparse observations We want to infer the conductivity across the whole plate. And so the top row here shows the solving a traditional Bayesian inverse problem with the Laplace approximation. The red is the true parameter that we're trying to find along this cross section here, and the black is the mean of that posterior distribution from the traditional Bayesian method. And then below, we show how our method performs. And so you can see that our method is performing better in the mean, and then also it still captures the inappropriate variance for the problem. That you can see the true parameter is still within a feasible set. The blue shows 3 sigma of the pointwise variance here. So this allows for us to rapidly estimate both the mean and uncertainty, mean and covariance of the unknown parameter u, given some new observations y that we're not seeing in the data set. And this is about 2,000 times faster than the traditional optimization method. You pay the cost up front in generating a data set and training a neural network, but then you have a rapid solver for these kind of inverse problems. Thank you.
Okay. Thanks for the great talk. Actually, that's great timing. Thanks. Appreciate like 5 minutes maximum. I hope the next presenters also stick to that. So next, we're gonna have Randall Ballestero. Randall, good. Okay. So he will talk about interpretable and learnable super resolution time frequency representation. Okay.
Thanks.
Okay.
Very happy to be here today to present the work we've been doing jointly with Professor Hervé Glotin and Professor Richard Baranyuk on proposing a new learnable time frequency representation. And just before introducing our method, let me motivate this research question. So if you take most of the state-of-the-art models, even in 2021, that leverage, for example, deep learning, you will notice somewhere in their pipeline that there is a time frequency representation, which is highlighted here in red. And basically what the time frequency representation is an image of a time series, which represents the evolution through time of the different frequency components that are present in the signal. And basically, this representation is not unique given a signal, but in all cases, they share the same type of information that they convey. Yet, different families of representation will highlight or dim different properties of your signal, and that can have an impact in your final performance. So, for example, if you want to obtain a wavelet transform, you will apply this type of filter bank onto the signal through 1D convolution. If you want to obtain a Gabor transform, you will use this filter bank. And if you want a chaplet transform, you will apply this filter bank. So you can see that different type of time frequency filters will react differently to different events present in the signal. Now, what you can actually do is reformulate how to obtain time frequency representation, not by doing this 1D convolution between those 1D signals, but by first bringing your signal into a new domain, which is done through the Wigner-Ville transform. And then in this domain, which is an image representation, you can think of it as a meta or a more general time frequency representation. In this domain, applying a time convolution with a 2-dimensional filter. And based on which 2-dimensional filter you use, the final result will actually recover the usual time frequency representation. And the key thing that we leverage in our method is that if you are interested in representation, for example, a Gabor transform, chaplet transform, or a Morley wavelet transform, then in the Wigner-Ville domain, what you end up doing is a convolution with a Gaussian, a 2D Gaussian filter. And the parameter of the covariance matrix and the mean parameter will define which time frequency you end up having in the end. And so what we simply propose is to make those parameters of your Gaussian filters learnable. And since everything is differentiable in those transformations, you will be able to adapt the type of Gaussian filtering you apply on the Wigner-Ville transform to better minimize your loss function at n. And through this, you will be able not only to move within a time frequency family, but also in between them. You can go from a Gabor transform to a Chirp-like transform to a Morley-Wavelet transform continuously, and you will do so to better solve the task at n. So I don't have the time to list all the benefits of this method, but I will just highlight a few here. The first ones are that you can actually exactly quantify the sensitivity of your representation to different input transformation or input noises as a function of the Gaussian parameters. So through this, you can impose some constraint based on some desired properties you want your transform to obey. And second benefit is that you can have improved classification performances when you use this method, not only instead of the usual deterministic transform, but also against other learnable methods. And I will conclude with this nice visualization on the right of the learned Gaussian filters on the bird activity detection task, where you can very easily and quickly interpret what has been learned. So here you see you are capturing some descending chirps for different frequencies. As you are in the high frequency range, you usually reach super resolution, which means you are very sensitive to input transformation. But in the more middle frequency range, your filters are trying to reach more stability to input transformation. You can see that through the increased area of your Gaussian filter, and you still have some descending and ascending chirp that are trying to be detected here. So if you have any other questions, I will be happy to answer during the Q&A, or you can also reach me directly. Thanks.
Okay, thanks. Yeah, indeed, we will have all questions in our Q&A session. Okay, so next paper will be, Hannah?
Yeah, can you hear me?
Okay, great. Yes, I can hear. Great. So,
great, thanks.
Yes, okay. So Hannah Lawrence will talk about the paper, present the phase retrieval with homography and unstrained piles. I think the title search there is going to have their application to the nanoscale imaging. Okay, please go ahead, Hannah.
Great, thanks. Yeah, as mentioned, I'm happy to give a preview today of our work on phase retrieval with holography and untrained priors. And so this is a fairly applied work, and the application that we're interested in is imaging nanoparticles. So specifically consider coherent diffraction imaging in which you have some unknown specimen, and from its diffraction pattern, you're trying to recover that specimen. So mathematically, this is the very familiar phase retrieval problem where you apply a twice oversampled Fourier operator, and then actually just from the magnitudes and not the phases of that data, you're going to try to recover the unknown specimen. And in short, recovery is possible, but highly ill-posed. And the experimental answer to that is actually to change the setup so that you get a slightly better posed problem. And that's where holographic phase retrieval comes in. And the idea is pretty simple. You're going to place a known reference object next to the unknown sample and try and use the interference between the two objects' diffraction patterns to simplify recovery for yourself. So mathematically, it's pretty fast to see that this is well posed. So here, X is your unknown object and R is a known reference. And if X and R are far enough away, when you take the Fourier magnitudes in real space, that corresponds to looking at the autocorrelation. And again, if X and R are well enough separated, the appropriate quadrant of the autocorrelation simply contains linear information about the unknown X, in particular, its cross correlation with R. And this is a linear inverse problem, which is pretty well posed under very easy conditions on the reference object R. Nonetheless, if I were to actually give you like real data from an experiment, there are still practical challenges for this problem, and that's what we're going to try to address. So first of all, it's a very high noise regime. The noise is not Gaussian distributed. It's actually distributed according to a Poisson distribution. This approximation only holds in the low photon regime. There's also a beam stop. So actually to protect the detector, you lose low frequency information. They're just occluded. And finally, due to physical constraints, you may not actually be able to place the reference object sufficiently far from the unknown object. So our guiding question in this work is how can we most practically apply modern ML techniques to experimentally realistic phase retrieval settings? And for us, practically crucially means data set free. So not just untrained, or not just unsupervised, but actually without placing any sort of data set assumptions on when you're imaging something de novo, what it looks like. So our method kind of combines two key ingredients. The first one is something very familiar, I'm sure, maximum likelihood optimization. And we're using actually the Poisson distribution on the noise because that's going to be the most faithful in the high noise regime. And the other ingredient is the deep decoder. So this may be familiar to some of you, but the deep decoder is essentially an untrained image prior invented by Heckel and Hand in 2019 that can output natural looking images if you optimize it appropriately, but again, doesn't have any sort of specific data set built into it. So we're going to restrict our maximum likelihood optimization only to images in the range of the deep decoder, i.e. only to natural images. And some intuition for what's happening here is that unlike linear approaches, which only leverage the linear cross-correlation information, we're also implicitly leveraging the nonlinear part of the autocorrelation in which X is convolved with itself. And the deep decoder is going to provide further regularization towards natural images. So we test this on a bunch of data sets, including some kind of more biologically realistic ones. And the data sets, again, are just for testing. In the paper, we have quantitative results and kind of more robust results. And here I'll just show you some pictures for the sake of time. We compared it inverse and meaner filtering, which are linear methods, as well as a variant of HIO, which is kind of the only nonlinear method that we could think to compare to. So first, one thing we can play with here is missing low frequency data. So here, as you move to the right along the columns, we're taking out more and more of the low frequency data and seeing which methods can still actually reconstruct this kind of cylindrical image. And our methods are here, the bottom two rows, where the bottom row also has the deep decoder. And just visually, what you can see from this is that as you go further and further out to the right, our methods can tolerate far more missing data than any of the baselines, which are shown in the top three rows. And that's kind of great news for experiments where you actually are missing a high fraction of the low frequency data. I'll just mention briefly, we can also break the holographic separation condition. So if you move your unknown object X really close to the reference R, linear methods don't even apply here, but we see our method in the very bottom row. It gets a very crisp reconstruction relative to the baseline on top. We can also play around with the oversampling rate. For the sake of time, I'll just move past this slide. And finally, since this is a highly experimentally motivated work, we thought we should also try it on some real experimental data. So here we have the reconstructions in the bottom line, and our method is all the way on the right. And we see that by both using the nonlinear information and regularizing by the deep decoder, we're able to get the best reconstruction on experimental data. So I'll end it there for the sake of time, but feel free to follow up with questions. Thanks.
Okay, thanks. Great. Okay. Okay, so next, I think we're going to have the actually last paper in this session on the, so we're going to have Terrence. Terrence, or go best there. All good? Okay, so.
You see
hello?
okay?
Yes, I can. We cannot see you, but we do hear from you. Yes. Okay. All right.
Can you see that now?
Yes, I can see the screen. Yes, good.
All right.
Okay.
Great. Yeah.
So Terrence also will present the work on multi-level stain variational gradient descent with applications to Bayesian inverse problem. Okay, please go ahead.
Okay, thanks. So this was joint work with Luca Venturi and my advisor, Ben Pierstorfer. And, sorry. So yeah, the main application that we consider in this work is inference for a Bayesian inverse problem, where we want to infer some unknown parameter theta, given some observed data y, which is the output of a forward model g. And if we have some prior beliefs about theta, then we can formulate a posterior pi in order to do uncertainty quantification. However, because this posterior depends on the forward model g, there are a few challenges. And first, if g is nonlinear, then the normalization constant for pi is unknown. And even more challenging is that g may be infeasible to evaluate exactly, meaning we also can't evaluate the unnormalized posterior density, which is required for many sampling procedures. So for example, g typically requires solving the exact solution to some PDE, which can only be approximated by numerical methods. However, oftentimes there's a sequence of surrogate models, GL, that approximates the forward model G, so that if G requires the exact solution of a PDE, then GL would require only the approximate solution using finer and finer discretizations. And the classical approach to inference in this case is to choose some high fidelity approximation GL, and then sample with respect to pi L by integrating with some particle method, which in this case we consider Stein variational gradient descent. And the main drawback of the classical Stein variational gradient descent approach is that it's expensive to integrate with respect to the high fidelity target for a very long time, which can happen if the starting distribution mu naught is very poor. So instead, what we propose is to use a hierarchy of surrogate models as preconditioners to find better starting densities for the following levels. So here you can see we start from mu0 and use pi1 to find a good starting density for the next level, and so on all the way up until we reach our target density. And the hope is that multi-level SVGD will drastically reduce the time needed to integrate with respect to the high fidelity target. And the first way we show this is through a theoretical analysis of the cost complexities, which are done in the mean field and continuous time limits. And this analysis relies on a few key assumptions. First, we place assumptions on the cost of evaluating each surrogate model GL, as well as the discretization errors. And next, we assume that SVGD converges exponentially fast, regardless of the starting distribution. And then we derive the following two results. So the first is that for a traditional single level SVGD, the integration time needed scales as the log of the KL divergence from the starting density to the target density divided by epsilon. And this leads to a computational complexity which scales as epsilon to the minus gamma over alpha times log of 1 over epsilon. And for our multi-level SVGD, we derive that the integration times needed at each level are actually constant, and that the computational complexity for multi-level SVGD scales as epsilon to the minus gamma over alpha. So we gain a theoretical speedup of order log of 1 over epsilon. And the second way in which we show that multi-level SVGD improves upon SVGD is through two numerical examples that are performed in the finite particle and discrete time setting. So here are the results that we obtained for a nonlinear reaction diffusion example. And the plot on the right shows the norm of the gradient versus the number of iterations taken, while the plot on the left shows the norm of the gradient versus the runtime. And you can see by looking at the dotted black curve that although SVGD converges in fewer total iterations, multi-level SVGD, which is shown in blue and red, is able to offload the bulk of the cost onto the lower levels, which makes it more efficient overall. And actually, by looking at this plot on the left, leads to an order of magnitude speedup. So thanks for listening, and hope you found it interesting.
Okay, thanks for the talk. Great. So I think we finished the quick presentations. It's a kind of a very fast pace. And I wonder, like, I saw a question in a Slack. So maybe, do you have any questions, like the authors for the other papers? Please go ahead. Okay. So at least I think first, I do have a question. As we have two works here, today we'll hear about two works on the Bayesian learning problem. I wonder, like, the maybe Terence still there?
Yeah, I'm still here.
Yes. Do you have any thoughts for the variation autoencoder paper? And I think that's by Jonathan. So do you have any comments about the approach and the application and so on on the topic?
Yeah, I mean, I think it's kind of two different approaches to inference, right? I mean, on one hand, you have these sort of parametric approaches like autoencoders and variational inference. And on the other hand, you have this sort of these non-parametric approaches like MCMC, or like Stein variational gradient descent, for example, which don't require a parameterization a priori. And so I think they're kind of like two ends of the spectrum. And I think they sort of maybe work well and they're kind of complementary, I guess is what I am saying. But anyways, those are just my thoughts on it.
Yeah, indeed. I realized indeed in within the maybe I missed some detail about your vibrational part. You already or also use something like deep neural networks somewhere in the same vibrational approach, or you maybe consider that also from your experience.
No. So the Stein variational gradient descent. We don't have
Itself that does not any neural network, of course. But yes, go ahead. Yes.
Right. Yeah. So ours is sort of. I mean, you could kind of think about it as, or at least how I think about our work is, it's trying to learn this transport map sort of non-parametrically. And this transport map is determined by this flow of the particles. There's no neural networks is, I guess, what I'm saying.
Yeah, I agree with Terrence. There are kind of two different complementary approaches to slightly different problems. Our approach is really useful if you know you're going to have to solve an inverse problem many times for many different observations. You want to solve it on the fly. It's very, very fast at that. But you do pay some cost up front, and it's a little less general if you have a different discretization, you have to retrain. It's yeah, there's just different approaches to a little bit different problems.
Okay, so I guess we have one more question from Jiahao Yao on for the what is the difference from original inversion problem? Like maybe the expert on Bayes inverse problem here can give an answer to that. Either Jonathan or Terrence or maybe anyone else.
Sorry, could you ask the question again? How's
So it's I think it's in the Zoom. So for the Bayesian inverse problem, what's the difference from the original inversion problem? Or maybe Jiahao, are you there? Can you ask your question again?
Yes. So you discussed about the Bayesian inverse problems. I just want to know what's the difference between this and the original, just the naive inversion problem. So is there any difference?
So ours is a little different in that you include this extra term that allows your solver to have access to the true parameter that you want, like actual samples. You consider them samples from the posterior. So you have like the Bayesian terms, we have your likelihood and prior, but then you also have you're matching your output to samples like real world data from the pairs that you have. And so each time you evaluate, you're not solving an optimization process, you're putting all the effort up front to solve one substantially larger optimization problem to optimize the neural network, but then you're just evaluating after that, and it gives you a mean and a covariance.
Okay, thanks.
Okay, we got one more question for Hannah. So
yeah,
Max, you there? Yes, go ahead. Yes.
Yeah, so Max's question was in the version of HALOP which does not include the deep decoder prior, which for us was kind of like an ablation. What prior is used instead for natural images? Yeah, there is no prior for natural images. So I mean, we called this like the pixel prior. You're just optimizing directly over the pixels dependent on the size of the image. And that's like, that's why we expect the deep decoder to do much better. And we do see that as well. So yeah, let me know if that answers your question. It's just directly a pixel prior.
Okay, so let's see.
I actually have a question for Anna, if there is just 1 minute. So I was wondering, why did you choose the deep decoder and not, for example, the deep image prior type of architecture? Is it because it's under-parameterized, or is there any specific benefit of the architecture of the deep decoder that made it preferable?
I think we originally played around with the deep image prior to, and just for the sake of having one, kind of zeroed in on the deep decoder because it seemed to be doing well. I don't know if any of my collaborators on the call have a different take on this, but yeah, I think I would expect the results to hold really for any natural image prior. So yeah, I think the short answer there is no. The important thing is just that it's untrained and that it actually can represent natural images, which most untrained priors would satisfy.
Okay. Okay. Thanks.
Okay. Okay. Yimin, okay, go ahead.
Yeah. Hi, Jonathan. So I have one question for you for your work. So in your work, you include a hyperparameter for your model that is the balance between the Jensen-Shannon loss function and the loss function of your data. So can you provide some insight about the choice of this alpha? So in your paper, I saw there. So in the experiment, you said that when alpha is greater than some level of greater than some number, then you said that the training is unstable. So can you provide some insight that what is happening there?
Yeah. So the choice of alpha, the definition of the Jensen-Shannon divergence is the sum of two KL divergences, and it's a weighted sum there. So your choice of alpha chooses which KL divergence you favor more. And so certain choices, one choice gives you a zero seeking like optimization problem, and then the other is a zero voiding. So if you have, for example, like a Gaussian mixture model with multi-modes, I believe we have this image in our paper with multiple modes. One of them is going to try and include all of the mass of all the different modes of the Gaussian mixture model, and another is just going to pick out one of them. We've found experimentally that we want to typically having a lower alpha yields better training, and you can see that in the results of the very last slide I showed today, that if you have a higher alpha is at the bottom, you end up being overconfident about something that's very wrong. Your mean estimate's not very good and you're very confident about it. So choosing a lower alpha we've shown experimentally that gives us better results.
Okay, thank you.
Okay, let's see if more comments or questions from the audience. So I think I do have another question, maybe related to Radal's work and also Amit's work. Radal or Amit still there?
Here.
So Randall, you mentioned the adaptive wavelet approach, I think, for your time series time frequency data setting. I was just wondering, have you ever considered also similar approaches maybe on the graph? For example, there are indeed graph wavelet approaches for other data type, I understand, not your immediate data type. And also that can relate to the graph spectral approach that Amit presented his work. I just wonder if you guys kind of have comments for each other on this aspect, or in any way to, consider the results or comments in this line. Yeah, that's the question. Kind of suggest if you have thoughts.
Yeah, that's a good question. So I think for the wavelet though, there might be some technical differences, because as far as I am aware on graph, for it to be tractable, you need to express it as a polynomial in Fourier. So I guess you have to do different type of formulations, but for sure there should be ways to adapt those methods on graph data. After all, what we are doing on time series is just a very specific type of graph, right, with regularly spaced nodes. So yeah, there is definitely a lot to do to extend those works.
Maybe I can say something about my work, is that what I was trying to say is that it's very beneficial to look at the matrix completion problem as an estimation problem on the graph. So once you look at it on the graph, then you can use anything you want. You don't just have to use the harmonic basis of the Laplacian. You can define any kind of operator there, and you can just apply the same kind of techniques that you apply on a regular grid in image processing, but now you do it on a graph. So you can use wavelets, you can use other bases, and yeah, surely you can benefit from that.
Okay. So let's see. With some discussion in the Slack. Is there any other question that we want to continue discussion here? Max, do you want to discuss here? I saw that you gave several comments there. Or any other question from the audience?
The discussion in Slack, I would say, fully answered my question, but maybe the thread can
Okay,
serve
cool.
for a little bit more.
Okay, cool. All right. Let's see. So, Lenka, when is the next session? Are we still here, or we need a break before the next session or something?
Yes, the next session is starting in 4 minutes, so we can take a short break if we don't have more questions.
If
at this
no more
point.
questions, but if there are any question from the audience, please go ahead. Yimin, do you have any other comments or?
Actually, I have no. I guess it's not that. I don't know if it is trivial. So
go ahead.
So it's a tourist. So in your work, so there's an assumption that about the exponential convergence of this. So in your paper, I saw there's about 6 assumptions. So I wonder if these assumptions can be relaxed or not.
Yeah, so the assumption can be relaxed. So the reason we included the exponential convergence rate for the SVGD was there are a few theoretical results which are kind of similar to that. I mean, both they have assumptions on the kernel for SVGD, where if you use a specific kernel, you can get exponential convergence. And also, I think there's starting to be some work in the direction for a discrete time setting. But you could also, like for our analysis, you could replace it with something slower than exponential convergence. I mean, the key here is really that both the multi-level SVGD and the SVGD are both, you know, it really depends, you know, if one is faster, the other one's also going to be faster, right? Because if SVGD converges at an algebraic rate, then it's also going to converge algebraically fast for multi-level SVGD, because you're still applying the SVGD algorithm just on different target distributions. And then it's also similar, the exponential convergence rate is also somewhat similar to like for Langevin flows. Typically, I think if like your posterior or target density satisfies like a log Sobolev inequality, then you can show exponential convergence rate for the Langevin flow.
Okay, thank you.
Okay, so if we're still allowed to ask one more question, maybe I want to ask Amit about the spectral graph, if he's still there.
Yes.
Yes, you actually continue the previous question. You mentioned that maybe graph, something like graph wavelet or other features can be adopted in your setting for your. I just wondering, because your paper is based on the spectral approach, essentially using graph Laplacian. What's your opinion about maybe the kind of the local filters for the graph data in your setting and in your
about
problem?
what? About
the
what?
The spatial constructions, just use the locality on the graph rather
right.
than
So isn't that I think this is encoded in Laplacian essentially, right? Because the Laplacian,
yes,
what it does is encodes this quadratic
yes.
form of, you know. So so I think, you know, the point is that you can trade locality. I mean, in image processing even, right? Instead of just using the regular grid that has nothing to do with the content of the image, you can just recreate a new grid, which is some underlying graph that depends on the content. And then you can have linear filters on this, or linear inverse problem on this graph, which uses some kind of a non-local grid, instead of a non-linear inverse problem on the original graph. So there is some trade-off. You're trading locality for linearity. And I found it very useful because you can just then apply very simple optimization techniques, you know, to solve this quadratic problem.
Okay, cool.
think
You
that
mean
this
by the energy approach? Yeah, by the derivative form approach.
Yeah, this is something that I've been plugging into many problems, and I found that it's always very helpful because it simplifies the problem a lot, and you can essentially get very good results compared to, you know, very complex architectures and very complex optimization schemes.
Okay,
Yeah.
great. I think we were running out of our session time, so we should give time to the next session. Thanks, Max. Thanks for all the speakers and the great questions. Thanks, Yimin, for the help. Okay.
Indeed, and thanks to you, to the chairs. And to continue the discussion, feel free to use the Slack. That's really